Welcome to our presentation, Preparing CySat 1, a look into Iowa State University's first CubeSat. My name is Matthew Nelson, and today we have Mackenzie Kilcoyne, Luke Gordon, and William Brown that will be presenting on our paper on this topic. I will now turn it over to Mackenzie, who will go over our agenda for this presentation.
Hi, my name is Mackenzie Kilcoyne, and I've been the project manager for CySat 1 for the last 2 years. Today we'll be going over CySat 1's primary and secondary mission. We'll talk about a subsystem overview for each component. We'll talk about the payload and payload testing in more detail. We'll briefly talk about obtaining licensing and the licensing requirements of the satellite. We'll talk about system integration and the various stages of integrating CySat 1. The facilities that were developed in order to create the satellite, the lessons learned in creating the first CubeSat from Iowa State University being a student-led project, and then closing with final remarks. CySat originally became a project at Iowa State University in 2004 when students started developing CubeSat components. Later on, this transitioned into a 1U project but could not obtain a launch due to unoriginal mission parameters. When students transitioned into a 3U project, the primary mission was educational for student experience. The secondary mission would be a technology demonstration for an SDR radiometer application that would survey soil moisture content in low Earth orbit. The mission will take approximately 3 to 6 months and happen during early 2021. Over 70 undergraduate students, several graduate students, and 4 faculty members have assisted the project over a few years.
Hello, my name is Luke Gordon, and I have been a team lead for the mission analysis and structured teams on the CySat project, and we will now overview the subsystems. The attitude determination and control system, shown in the upper image, is from CubeSpace. It contains CubeSense, which is 2 CMOS-based sun and earth sensors, along with 5 sun sensors and a magnetometer sensor. It runs on 7.4 volts, thus requiring a boost board with the current electronic power system. The EnduroSat EPS Type 1 Plus fulfills mission power storage requirements and is certified to travel to the ISS. It outputs 5 volts and 3.3 volts and also has monthly battery health checks. Its electrical bus uses the PC104 connections for power and information transference. The antenna and radio went through multiple configurations. The first configuration was a tape measure dipole antenna with a AstroDev radio. However, the radio did not support the new protocols and caused issues during licensing, as well as the antenna fasteners and the antennas were not compatible with the structure. The second configuration is the EnduroSat UHF antenna and transceiver. This is specification compliant with the antenna as it fits within the structure, as well as the radio can be adjusted in-house as opposed to at the manufacturer to fit the assigned frequencies.
The onboard computer, or OBC, serves as the brains for CySat 1 and talks to the various subsystems that we have. This includes our attitude determination and control system, our power system, our radio system, and of course the payload. The students began originally by wanting to design and build their own OBC. This was going to be built around an STM32 microcontroller. However, as time progressed, the students realized that undertaking such a daunting task was going to very much extend the timeline for the satellite. Therefore, a decision was made to go ahead and purchase an off-the-shelf solution. This would be the EnduroSat OBC that we are now using in CySat 1. In all the cases, we wanted to have a system that used the PC104 connector, and the EnduroSat OBC used that. It also allows us to talk using standard communication protocols. This includes I2C, SPI, and of course RS-232. With that, it also utilizes an STM32 microcontroller as well. And since the students are already familiar with this microcontroller, making the jump from their own built solution to this solution would be a lot easier than jumping to a completely different architecture. With also moving to this type of system, the students could now focus more on the software side of things. They could work on developing the firmware that would allow the OBC to talk to the various subsystems, and they also could focus more on the software that needed to be developed for the payload as well.
The structure was designed, fabricated, and assembled in multiple parts by students. The structural rails were cut from aluminum 6061-T L-channel and then hard anodized per industry specifications. The 4 anchor plates, which hold the threaded rods for all subsystems, attach the rails with the solar arrays. These anchor plates are 1/4 inch thick aluminum plates. The structure supports all critical systems and follows CubeSat specifications and allowed hands-on experience for students.
The payload on CySat 1 will use a software-defined radio radiometer. This type of radiometer uses a few components that are found in a typical radiometer, mostly the fact that we have an amplification system that boosts the signal up so that we can easily detect it. This is done using low noise amplifiers, and in our design we have a 3-stage or 3 LNAs that are chained together. With that, once we amplify the signal, however, we immediately digitize the signal. And in our case, we're preserving both frequency and power information. And I'll explain why in just a little bit. Once we have that, we are now doing everything within software. Everything that we define with the radiometer is now defined within that software as well too. Any kind of filtering that we might need, any kind of integration can now be done. And this is one of the reasons why our system preserves frequency information. By preserving the frequency information, we can do filtering both on a within the band that we're interested in, but even narrow band filtering as well too, if we have something like an interfering signal that is detected. We can also implement some other types of radiometers, which again would be either difficult or almost impossible to do on a more traditional radiometer. Finally, this is a demonstrator for us. We are testing to see how well this system works, and especially in a confined space like a CubeSat satellite. So we're hoping that with this we learn quite a bit on how we can implement these, and maybe these could be used on future CubeSat missions.
Hello, I am William Brown, an undergraduate member of CySat, who designed, manufactured, and helped test the payload antenna, as well as the payload system as a whole. The payload antenna is based off of a stacked shorted annular patch antenna, which was picked because it should produce the theoretical gain as well as be easy enough to manufacture. The CAD model that was designed was analyzed using the program HFWorks, and the physical antenna itself was constructed at Iowa State University using solder paste adhered to the joints and eventually put into a reflow oven. The goal of this antenna was to maximize gain as well as to fit within a 1U space. The physical testing of the antenna was conducted using an anechoic chamber that was also produced at Iowa State University and shown in the picture in the left. The black material you see is the RF absorbing material that was adhered to the walls of the chamber. Leak testing was performed to ensure that the antenna is isolated within the chamber itself and that no outside noise affects testing. Testing was then performed on both sand and soil with varying levels of water content at standard temperature and pressure, as well as submerged under liquid nitrogen.
Licensing of CySat 1 was definitely no easy task. At first, CySat 1 was an amateur project, being primarily led by students and the primary mission being for student experience. It was coordinated with NOAA in August of 2018 and shortly thereafter coordinated with the IRU in October of 2018. CySat 1 operates under Part 97 of the FCC rules, which align with amateur status. The integration of CySat 1 took place over 4 phases to check each aspect of integration. The first phase was the primary fit check of CySat 1, taking place from September to October of 2019. This was the first dry fit, ensuring proper fitting of all system components and verifying spacing, measurements, and tolerances. The second phase took place from October to February of 2020, which we took a closer look at the wiring in preparation for a power-on test. Phase 3 would be that power-on test, ending with a mock launch, mock mission, and an alpha software for both the satellite and ground station to be completed in October of 2020. The final phase would be final integration, finishing in January of 2021, which would finish in a vibration test, hardware and software freeze, and handoff.
CySat has used multiple facilities to build the satellite. Shown here is the Make to Innovate lab pictured in the bottom left, along with the anti-static room pictured in the bottom right. The Make to Innovate, or M2I lab, provides a hands-on workspace and tools which include 3D printing, power tools, computers, and electronics workstation which includes soldering stations and test equipment. CySat designed and assembled different subsystems in the lab along with its initial integration, including the first dry fit. The anti-static room is used as a space hardware test space in the M2I lab. It is a separate space which reduces dust and particle contamination from equipment in the general lab. It contains properly grounded workstations and is also used to mitigate potential electronic and system problems and validate new methods. The Cardinal Space Laboratory Cleanroom, shown in the upper image, is a 130 square foot cleanroom that provides a large work area for integration and assembly of sensitive components. The frame of the cleanroom was constructed out of 80/20 aluminum along with acrylic panels, with easily cleaned antimicrobial flooring. It maintains its air quality through two HEPA 0.3 micron fan filter units. The workspace includes electrically grounded workbenches and dedicated storage and testing equipment for electrical systems. CySat will utilize this space for solar array assembly and for final integration. This gives students experience with working in a cleanroom with sensitive components and systems, thus enhancing their educational experience. Many lessons have been learned throughout the CySat project. For project goals, industry licensing and specification requirements were hard to navigate at times. Also, class requirements varied from semester to semester. The lesson learned was better research and communication would have allowed better goals to be set and built upon each semester. For mission planning and the timeline, progress on the project was overestimated for undergraduates working part-time only. Also, the depth and scope of the project was underestimated at the beginning. More obtainable goals and milestones were set once this was realized. For the capabilities and coordination of the team, no official process for knowledge transfer between veteran members and new members was set at the beginning of the project. Also, the lack of facilities at the start hindered the project. The project was supplemented with a variety of engineering disciplines, and an official knowledge transfer process was initiated to mitigate some of these problems. This allowed more progress to be completed on the project.
Other lessons learned had to do with coordinating our radio to meet IARU and FCC coordination requirements, and then integrating commercial off-the-shelf components into our own in-house designs. We had to refabricate the structure on a number of occasions in order to meet the tolerances of commercial off-the-shelf systems, and thereby also redoing software requirements. Due to a lack of early written documentation on the project, a new project culture had to be implemented, which was especially important going toward the COVID-19 pandemic and further delaying our handoff. In closing, CySat 1 is currently in Phase 3 of integration. This has been delayed due to the COVID-19 pandemic and the slow reinstatement of laboratory access to students, thereby preventing them from accessing hardware during this time. A preliminary timeline for CySat 1 sets a completion date of early 2021, setting up for a May launch. In closing, students gained a variety of experiences with this project, primarily in hands-on application and project management. The facilities developed will set up the program for future endeavors. This mission will demonstrate the software-defined radiometer for its use in further applications later on, and the documentation will aid future teams in developing a CubeSat much faster and more efficiently than we had done in the past.
Thank you for watching our presentation. We hope you enjoyed everything that we presented, and as you can see, CySat 1 is on its way to being launched, and both the faculty and the students have learned a tremendous amount from this experience. I have also put my contact information on this slide as well. If you have any questions, please ask. We'll be more than happy to answer them. Thank you.